scientist at the Qatar Computer Research Institute. Before he was a senior research scientist in ISTI in CNR, Italy, and a professor in the University of Padua. He's, of course, very well known about his seminal work in text classification, mining, opinion mining, well-known centi-wordnet. Has written a really large number of high-impact journals and articles, and also has given very insightful tutorials in the area. So we're really honored by having you here and give us this very interesting talk.
Thank you. Can you hear me in the back? Okay, good. So, well, I'm really honored that you invite me, actually. So, I mean, this lecture is going to be about, well, text classification plus sentiment analysis and opinion mining. Okay, so these are two areas that are seemingly pretty far away, you know? But I mean, the connection will become clear during the lecture. First of all, I mean, the lecture is. I'm happy for the lecture to be interactive. I mean, so you can interrupt me any time you want, you know, for questions and the like. So the lecture also will be fairly introductive. Okay, so it will not be, I mean, that advanced, in the sense that, well, my goal would be, you know, for 80 or 90% of you to understand 80 or 90% of the material, rather than for, you know, 10% of you to understand 100%. Okay, so can we turn the lights down a bit? So let me start with the text classification part. So text classification is a fairly time-honored discipline, in the sense that unlike sentiment analysis and opinion mining, it was, you know, born long ago, and there is quite a big amount of published work starting from the early 80s at least. So this will be roughly the structure of my talk. I will first, you know, give a bit of introductory background on what the task consists of. I will look at a number of applications, and then I will look at the basic approach that we need to take in order to set up a text classification work. So you might understand this to be a sort of a blueprint of how to go about doing text classification. So there are two main parts in using the supervised learning approach to text classification, which is basically not just training classifiers, but preparing, you know, representing the text code for classification purposes. So I will also touch on evaluation, which is often a critical point, you know, because, you know, several text classification papers in the past have been, you know, rejected because of choosing the wrong evaluation measure of alike, you know. So that's essentially an important point. And I will briefly touch on some further advanced topics. So classification, I mean, we've heard about classification several times during this school. It's essentially a ubiquitous enabling technology in the whole of data science. I mean, people have said that classification now, I mean, should be taught in undergraduate courses, you know, in the first year along sorting and searching. Okay, and probably this is not too far away from reality. It's been very, very well studied, you know, within pattern recognition, statistics, machine learning, and of course, I mean, classification goes much more back in history to the ancient Greeks, you know, with Plato and Aristotle, you know, who actually discussed the problems of classification well before, you know, computers and pattern recognition was invented. So essentially, classification is the activity of predicting to which, among a predefinite finite set of groups, which we call either classes or categories, or codes sometimes, a certain data item belongs to. Okay? And so here the emphasis is the fact that this set should be predefined. Okay? So it's we normally formulate this as the task of generating a classifier, which typically in IR we use the word classifier, but the machine learning people tend to call it a hypothesis or a model. So this classifier has this form, so it essentially maps a given document into a certain category, where documents have a certain vectorial representation that we here indicate in boldface, and we have this finite set of classes that we often call the classification scheme. In our disciplines, it's called a code frame or a code book. So it's essential to realize that classification is different from clustering. I'm saying this because there is some confusion in the terminology, especially in other disciplines where clustering is indeed called classification. Okay, so we all know that clustering is something different, is something where, sure, I mean, you attribute data items to groups, but the groups are not known in advance. Okay, and it is sometimes the case that you don't even know the number of these groups. So classification as we see it here is quite different because we know the classes, we know their numbers. And text classification is simply the situation in which data items are textual, So this is traditional textual items such as news articles or emails, but in many IR applications we are seeing applications where we are talking about much smaller data items such as queries, named entities, or the like. Or sometimes, I mean, these documents are just partly textual or more than textual, such as web pages. Web pages, they all have a lot of different stuff aside from text, such as video, images, and hyperlinks. So we normally talk of classification when the membership of a data item into class cannot be determined with certainty. Okay, so sure, I mean, putting natural numbers into class prime or non-primes is putting data items into groups, but this is not what we call classification. So it is essential to the notion of classification that there shouldn't be an algorithm that allows us to determine with certainty if the item belongs to the group. And it's also essential to remember that there are many different types of classification. So the very simplest case is binary classification that we all know, So the idea here is that essentially for each document, we have to attribute to each document a single category where the possible number of categories is just 2. And I would like to say that binary classification is not so simple because there are sort of two different views of binary classification. One, which is more typical from information retrieval, which sees binary classification as classifying C versus not C, so a class versus anything else, While there is a more machine learning type view, which is C1 versus C2, where the two classes tend to be on the same level. And of course, the idea is that the information retrieval view is actually biased towards a notion where binary classification is classifying signal versus noise, where we typically have a very small quantity of signal, the relevant documents, and a very, very large quantity of noise. Okay? So this has generated, two slightly different ways of treating binary classification, especially when it comes to evaluation in the two different fields. So one typical, application from information retrieval is, say, assigning emails to either spam or legitimate. So a different type of classification is single label multi-class. Okay, so here the idea is, again, that we need to pick a certain class for a given document, but each item belongs to exactly one class, but we have n classes with n higher than 2. Here, essentially, label refers to the fact that a class is attached to a given document. Okay, so single label means each document can have only one class, but it is multi-class in the sense that we have several different classes from which to pick. And here, well, one idea could be, say, assigning news articles to one of the following classes, say home news, international, etc., in order to decide, say, in which page of the newspaper to have the article printed. So a slightly different type is multi-label, multi-class. So multi-label refers to the situation in which you can assign, so it's still multi-class, we have more than one class, but we can assign more than one class to the same document. Okay? So this is a typical situation, say, when we write a computer science article and we need to assign the article to different classes in the ACM classification scheme. So we typically come up for several classes at the same time for the same article. So each item in general may belong to 0, 1, or several classes. 0 means that the article is relevant to no class in the classification scheme. And the tradition in multi-label, multi-class is to simply solve the problem as an independent binary classification scheme. So for each class in the classification scheme, we actually use a binary classification to decide whether the class applies or not to the same document. Currently, there is one of the advanced topics that I will mention at the end is the fact that there is let's say, an increasing amount of literature in trying to, let's say, waive this assumption and try to actually learn to actually solve the multi-label, multi-class problems without really seeing these as independent binary classification problems and trying to leverage on the stochastic relationships between the different classes. Finally, one increasingly important problem is ordinal classification. So ordinal classification is still a single label problem. It's still a multi-class problem, but we here assume that the classes are ordered. So there is a total order among the classes. So one typical case might be excellent, good, so-and-so, poor, disastrous. Disastrous, yes. So, which is typically the case of product reviews which are evaluated or evaluated according to such a scale in say Amazon or other product review sites. In general, ordinal scales have been extremely popular with the social science people because every time you elicit judgments, okay, sort of a qualitative judgment from people, I mean, social scientists have sort of shown that ordinal scales are actually the ones that are most reliable. And ordinal classification tries to automate this process. So, I mean, the definitions that I have given here denote what we call hard classification. Hard classification is when we have to firmly assign one or several classes to a given document. But there is a version, a different variant of classification that is sometimes called soft classification or ranking classification, and instead denotes the task of predicting a score for each pair consisting of a document and a class. So the score might denote, say, the probability, the posterior probability that the document belongs to the class, or as we might call it, the strength of evidence that the document belongs to the class, the confidence that the system has in the fact that it belongs to the class. So we normally talk of posterior probabilities when the classifier is probabilistic. Okay, so this is indeed the posterior probability output by the classifier. Not all classifiers are probabilistic. Say AdaBoost, is a classifier that outputs scores which range on minus infinity and plus infinity. And again, I mean, these represent the confidence that the document belongs to C. And, when these scores are not probabilities, you can indeed convert these into probabilities by the use of a sigmoid function like this. Okay, so sigmoidal functions are functions that convert the real scale interval monotonically into the 0-1 range, so they convert them into probabilities. And in order for these to be good, let's say good probabilities, we do something called calibration, which is basically checking that the average posterior probability that results from the conversion is actually coincides with the fraction of documents that do have the class in the set. So hard classification, so the firm assignment of documents to a class, often is soft classification plus another phase, which is, let's say, using a threshold. So typically when we train a hard classifier, we might end up in training a soft classifier, say a probabilistic classifier that outputs scores, and then picking a threshold T, such that each score that exceeds the threshold is interpreted as a yes, the document has the class. And each score that is below is interpreted as a no. Okay? So typically in soft classification, there is no need to generate thresholds because these scores are used for ranking. Okay? So you may have document ranking, which means take a class and rank the documents in terms of their fit to the class, or you might have category ranking, which is more used, which means take a document and rank all the classes in terms of how well they fit the document. And typically, hard classification is used when you want to have fully autonomous classifiers, okay? Classifiers that don't require any user intervention. While soft classification is used for interactive classifiers. So classifiers where you have a human in the loop that maybe in critical situations wants to check the result of the classifier in order to validate it. And soft classification approaches are, of course, ones where the classification decision has a critical value, so there is a critical application where you often don't want to get mistakes, So usually, when we talk of text classification, we all think of classification by topic. Okay, so taking a news article and deciding whether it's sports or home news or politics. But this is not always like that. Okay? So there are several dimensions or axes, as Carlos Castillo has called them, which are orthogonal to each other, and dimensions according to which we might want to classify a document. So typically, the default, our default assumption is that we classify by topic. Okay, so this is by far the most frequent case. It has ubiquitous applications, and this is indeed the case. News articles in sports or home news or etc. One important class to which I will devote the second part of this lecture is classification by sentiment. Okay, so essentially, in classification by sentiment, we take a piece of text which typically is rich in opinions, which we know to be, say, about a certain object, and we need to decide whether it expresses a positive or a negative view about this object. So it's classification by topic and classification by sentiment are completely orthogonal. Okay, so it should, and all of these dimensions that I'm talking about, are completely orthogonal. So another type of classification is classification by language. Okay, so sometimes this is called language identification. So given a text, we need to figure out, whether it is in English or in Spanish or in Russian. Okay. So this is usually considered pretty easy as a task, unless the documents are very short, okay? Because with the short documents, say tweets or queries, the amount of information that allows you to work on the problem is very small. So language identification, as we have heard in previous lectures, is useful in query processing within search engines, okay, where you have to decide which language which language it is in order to best process it. In some applications also, classification by genre is interesting. Say we might want to classify for, say, market research purposes, we might want to classify websites into some rich taxonomy that maybe distinguishes between automotive news versus automotive blogs. And so, I mean, this is something that really cuts across topic, okay, and that invests the very notion of what the document is for, you know. Another type another group of dimensions are interested especially in forensic applications. So classification by author. So this is called authorship attribution. And the idea is you have a text of unknown authorship, so disputed paternity, and you don't know who the author of the text is, and you have k potential candidates. And you might want to figure out who among these people actually wrote the text. So, I mean, the applications are not, you know, detecting whether a sonnet was written by Shakespeare or Marlowe, but the typical applications are in forensic, say, cyber terrorism, figuring out, you know, the kind of person who has written this. And there are variants of this, okay, so classification by author, but also classification by native language. So there is a shared task on this, which has to do with the fact whether, you know, a certain piece of text which was written in English but by a non-native speaker was actually written by someone whose native language was Indian or Urdu or Spanish or Chinese, you know. And classification by gender has been applied too. There are scores of other dimensions, okay, including classification by usefulness, okay, detecting whether a certain product review is, you know, is useful or not. Martin has talked about classification by intent for queries, etc. So, I mean, these are kind of distinctions that we always need to, you know, keep in mind, I mean, when approaching a certain classification task. So let's look at application. There are really scores of applications in text classification. As Katya mentioned this morning, probably the first application for text classification was libraries, you know. Well, not just libraries, but also digital documents. Okay, so in the early days, probably, I mean, you don't remember, you weren't around, I mean, during these early days, but information retrieval systems were Boolean. So were based on the fact that each document was assigned a set of descriptors, okay, which described its semantics. And these descriptors were taken from a controlled vocabulary, a fixed set of words, controlled vocabulary that we may equate to a classification scheme. This was an activity which was performed by humans, you know, and it was, of course, expensive. So the early research, especially in the 80s, and I would say especially by the group of Norbert Fuhr in Dortmund or Darmstadt, or where he was at the time, so that the early work on text classification was done when text classification was not called like that. And if you search for text classification, Norbert's work will not come up because it was called automated indexing at the time. And so, I mean, this gave the initial impetus to this work. The second wave of impetus came in the late 80s or early 90s, where companies like Reuters, okay, actually tried to figure out a way to automate the process of selective dissemination of their news articles to different subjects involved. Okay. And selective dissemination means, well, if a certain news article is about a certain topic, I will send it to this subject, or let's say, I mean, if the news that should be sent to this subject are the ones that deal with this and this and this topic. Okay. So classification is again at stake here, And actually Reuters, Reuters, the news agency, has a very important place in the history of classification because, first of all, in the late 80s, it gave impetus to research in text classification by first funding the production of an automated text classifier and by also releasing data. Okay, so essentially what has come to be known as the Reuters collection, or now Reuters 21578, is probably the first important data set from the history of text classification. It is essentially a set of news wires classified according to different economic topics. Okay. So in general, I mean, these applications to libraries or to news articles fall under the head of what I would call knowledge organization. Okay, so organizing an unstructured body of knowledge for the goal of making the access to this body of knowledge more effective than if the body of knowledge were unstructured. Okay, so I mean there are again scores of types, of instances of using classification for knowledge organization. And here I've already talked about the Reuters case, about the scientific papers. Classifying patents is very important nowadays because, I mean, patents, I mean, there are huge numbers of them, and it is very important for two reasons. Okay, so first of all, I mean, when a patent is incoming, is submitted to a patent office, the patent office needs to find out who the best examiner for this patent is going to be. So it will classify the patent, trying to find out a primary category for the patent. And since the office has an association between primary categories and people, so the examiner will be chosen. The second reason why patent classification is important is that when the patent needs to be, deposited, archived, it gets archived under a certain number of classes so that people in the future, when looking for prior art, when looking for inventions about a certain topic, will be able to discover this patent easily. So I mean, classifying patents is one of the biggest, most important applications of text classification today. Others are, say, you can classify classified ads, like for assigning to Craigslist, and in market research, and we will come to this, you can automatically classify answers returned to open-ended questions within surveys. Classifying topic-related tweets by sentiment is also big, and we will also come to this. In theory, in the past, it had been suggested that retrieval, as in ad hoc retrieval in search engines, I mean, could also be viewed as binary soft classification into relevant and non-relevant. But this is, in the past especially, it has been more in theory than in practice, in the sense that you always need training data, and you don't always have the training data for each query, So a second class of application is what we call filtering. Filtering, or sometimes also called routing or routing if you are American, So filtering normally refers to the activity of blocking. So when you have an incoming stream of documents, blocking non-relevant documents and allowing only relevant documents to pass. So typically this is a dynamic stream, and so one example is, say, you want to run a social study using Twitter about the sentiment of users towards ISIS, then, well, essentially tweets that are not about ISIS need to be filtered out. Okay. Of course, I mean, spam filtering is one probably the foremost example of filtering. Okay. And the spam filtering, but also all of the applications having to do with detecting unsuitable content, as in parental guidance filters or social media. Okay, so filtering porn, filtering violent content, racist content, or cyberbullying, etc. So all of these, I mean, have to do with filtering. And a third class of application that I would like to mention is, applications that we have seen throughout all of the lectures up to now. So classification used in order to empower other IR tasks. Okay, so viewing classification as an enabling technology ancillary to improving the effectiveness of these tasks. So over these lectures, we have seen, classifying queries by intent within search engines, but there is also a very similar application in question answering, where you want to classify questions by type, whether it's a where question or a why question or a question or a search for a definition, for instance. So classifying questions by type in these kind of query answering systems. Classifying named entities has come up too, but also, in say NLP applications, doing say word sense disambiguation, okay, which is a text classification activity too. So one of the differences between these tasks we are seeing in this slide and the previous one is that here we are mostly talking about very small text such as queries, questions, sentences, etc. While typically up to now we have seen applications to longer texts. So essentially the history of text classification is a history in which probably at the turn of the 90s, between 80 or the 90s, okay, so the supervised learning approach started to be the main approach. Okay, so before this, especially in applications, well, Reuters was a main example. So still the let's say old-fashioned way of building text classification engines was used, which was via knowledge engineering. That means essentially manually engineering rules, okay, by taking a domain expert that writes, say, implications such as, if you, in a message, you detect either the word Viagra or you detect the word sildenafil or Cialis, assume that it is spam. Of course, this approach of going about building text classifiers has disadvantages, okay, because it's very expensive to set up, because you need an expert to write all of these classification rules, and it's also very expensive to maintain. So what about if you want to introduce another class in the classification scheme at a later stage? Okay, what about when text? The types of spam, we know that they evolve very quickly. Phishing wasn't around at the time at the early days of spam. Okay, so this is an approach which has lots of dramatic disadvantages. And in the let's say in the 80s, the supervised learning approach was used. We have mentioned the work by Norbert Fuhr, but it had not yet been detected by the industry. It started to be detected or recognized by the industry probably as a result of people using the Reuters collection. Okay, so the Reuters companies started to note this work, and other companies followed suit. So I would say that in the 90s, the 90s are the years in which the supervised learning approach becomes dominant, and essentially these companies actually come to recognize that the approach has several advantages. Okay, so especially the fact that generating training examples is much cheaper than writing classification rules. Okay, and this has a background in cognitive science too, because cognitive science basically says, findings within cognitive science that say that when you want to characterize a concept, it is much easier to characterize it ostensibly, they say, okay, by, let's say, pointing at examples of the concept, rather than characterizing it intentionally. Okay, so describing rules for recognizing instances of concept. So it is much easier to point at a set of red objects rather than writing a rule for recognizing redness. So the supervised learning approach that we all know came into existence within the text world and became dominant. So this is let's say the architecture of a typical, very typical text classification engine, where essentially you have a classification scheme where you have a number of training documents that are fed into a module that extracts content, that reduces, that maps a given document to a vectorial representation. So the vectorial representation of training documents are, together with the classification scheme, are fed into the classifier training module. So when the classifier is trained, this is fed to a document classification module that takes into, as input, the result of the content extraction of unlabeled documents. And here you get the automatically classified documents. Of course, you can get further loops. So one is actually shown here, in which you say you might want to validate, a human annotator might want to validate some of the choices, of the classifier. This is what is called, actually, when there is an algorithm that actually suggests to the annotator which documents to validate. This is what we call active learning. So let me just briefly go into the content extraction part. Okay? So, as we all know, in order to be input to either a learning algorithm or a classifier, we need to convert all of our training and unlabeled documents into vectors in a common vector space. Okay? And we call all of these dimensions features. And there are three basic steps that we need to carry out. One is feature extraction. Then we have an optional step which we call feature selection or feature synthesis, and then we have feature weighting. Okay. So in terms of feature extraction, in classification by topic, and I want to stress here that we are talking about classification by topic, here a typical choice is to use the so-called unigram model or bag of words. This is a model that all or most of us know. So the idea is that we need to extract from documents all of the words that occur in the document and in the document set. Okay? So an alternative choice to the bag of words or unigram model is to actually also extract n-grams. Okay? So sequences of n words that occur frequently in D. Okay? With the idea that these frequencies, that these sequences, such as, these might be noun phrases that carry a specific meaning, that have a small degree of compositionality. So, with the idea that these phrases might bring in additional semantics. Okay. So of course, the big problem is that if there are a lot of unigrams, okay, there are even many more, bigrams, and so the problem gets easily out of hand. Okay? So the dimensionality of the vector space might become too large. Okay? So typically, if a unigram plus bigram model is used, only the most significant bigrams are actually added. Okay? So of course, what we do, like in all other IR endeavors, we do stop word removal and stemming. Okay, where stemming is mostly used in order to improve the statistical robustness of the counts. But I want to stress that this choice is a typical choice only when we do classification by topic. Okay. And I will come to other dimensions of classification later. So another alternative to this, as some of you might have encountered, is to actually use as the set of features, to use character n-grams. Okay, so that's sequences of not just a word, but sequences of characters that occur frequently in our text. And the very idea is that this might be very useful, especially in texts which are highly corrupted, which are highly known, where there are lots of typos, especially due to phenomena, due to maybe the source where these texts come from, which might be optical character recognition or automatic speech recognition. Okay. So in order to of course, I mean, in order to achieve statistical robustness, all of the tasks that we have seen up to now completely renounce to encoding word order and syntactic structure. Okay, because the idea is that if you do try to encode this, I mean, your dimensionality will increase even more, your robustness will go down. As I said, I mean, these kind of choices, which are sort of the default choices that many of us or all of us know, are only okay for classification by topic. Okay? So when we need to attack other dimensions, okay, we need to do a careful and a different type of feature design. Okay? So the idea is that the choice of features for a given classification task is dictated by the distinction that we want to capture. Okay? So suppose that we want to deal with authorship attribution, so classification by author. Should we still use bag of words? Of course not, okay, because I mean, two authors might speak about the same topic, okay, so I mean, the kind of content-bearing words that we use in classification by topic would be pretty useless here, you know. So the idea is that in classification by author, we use, you know, type of features that we completely disregard when we do classification by topic, okay? And so features that tend to try and capture the kind of style, that the writing style that the user, you know, adopts. So, I mean, features such as average word length, you know, because the more educated the person is, the more long words tends to use, okay? Average sentence length, similar motivation. Punctuation frequency, punctuation appropriateness, you know, frequency of subjunctive clauses, okay? There are scores of these, of features like this, which no one would ever use in classification by topic, but they are of fundamental importance in classification by author. So this basically shows that, you know, feature design, the choice of features is really a kind of art that the text classification engineer must really devote to, you know. So in another example is classification by sentiment, okay, because classification by sentiment is an application where a bag of words doesn't lead you anywhere, okay, because if I want to say review a certain hotel, I might say, well, a beautiful hotel in a horrible town, exclamation point. But that would be the same as, you know, a horrible hotel in a beautiful town. Okay, same words, but completely different meaning. So, I mean, feature design is important, especially when, you know, change different, the dimension that you actually use. Okay, so I think I need to go a bit faster than I have been up to now. I just want to mention feature selection, which is important. You know, feature selection is let's say it's a step which is especially important in text classification, while it might not be as important in other classification endeavors, especially because in text, you know, the dimensionality of the vector space might be enormous, you know. So the idea of feature selection is that you want to try and figure out which features are the most useful and discard the others, okay? So there are essentially two reasons why you might want to discard them, okay? So one is high computational cost, of course, I mean, because the cost is proportional, you know, to roughly proportional, I mean, to the length of your vectors. And the second is overfitting, okay? Because overfitting is, for those of you who don't exactly know this notion, is a problem that kicks in when you have an under-constrained problem, okay? So essentially here, you know, classification is a problem where you have a number of variables and you have a number of constraints on these variables. So the variables are your features and the constraints are your training examples, okay, which give meaning, you know, to these features, okay. But typically you have a much smaller number of examples than features, okay. So you have a completely under-constrained problem, okay. So in order to make this problem less dramatic, you try to, you know, discard a number of features that are deemed less important. So typically, the approach here that is used is what people call the filter approach to feature selection. So the idea is, let's take a feature one by one, let's give a score to each feature, and let's retain only the highest scoring features. And here there are lots of functions that have been dealt with in the literature, for actually giving these scores. The popular functions are information gain, mutual information, chi-square, etc. So something that should be noted again is that for each classification task, some functions might be appropriate and some not. So especially if you want to use ordinal classification, so if ordinal classification is your task, then you have to go for feature selection functions which were specifically designed for ordinal classification. So I think I want to skip a bit the issue. Well, no, I mean, let's matrix decomposition. I don't want to skip feature synthesis because it relates to a topic that Katja mentioned this morning. So the idea of feature synthesis is to try and replace the original words or the original individual features with a number of syntactic features. Why should we want to do this? Okay. Well, I mean, because when we use the individual words, there is a lot of maybe synonymy, or ambiguity between them. So the idea is that we are going to work in a vector space where, the axes are orthogonal, but they shouldn't really be, because they have a lot of stochastic dependence between them. So the idea of, for instance, matrix decomposition techniques, which are latent semantic indexing, which in turn relies on singular value decomposition, but principal component analysis are others. So the idea is to convert the original vector space into a smaller dimensional vector space, which doesn't suffer from problems like synonymy and antonymy, etc. So I want to highlight this because this is an example of techniques which bring to bear the notion of distributional semantics that Katja mentioned this morning. So distributional semantics is a very old theory in linguistics, which goes back to at least the 50s, which essentially says, the meaning of a word is the word it goes together with. Okay, so co-occurrence of words is fundamental to our understanding of the meaning of words. Okay, so essentially all of these techniques try to leverage on the word co-occurrence in order to figure out their meaning. Okay, and the advantage of these techniques is that the syntactic features they generate do not suffer anymore from these problems such as synonymy and ambiguity. The disadvantage, the reason why they are not ubiquitous, okay, in text classification applications is their high computational cost. The idea of word embeddings that many of you might have heard, which is recent, which Katja also mentioned this morning, actually relies on distributional semantics too, and it's probably what we might call the new wave of the use of distributional semantics within text applications. Feature weighting, you probably know everything about feature weighting or almost everything. Okay, so we all know that it is best for accuracy reasons. Okay, so to weight the contribution of a certain term in a certain document, and we all know that these often occur happens via functions such as TF-IDF